Okay, so let's begin this. If you don't know, over on my Twitch channel, where you are watching right now, if you are with me live, I do these discussion series every Wednesday where we work through a topic. Right now, currently, we were working through quantum computing. If you're in chat right now and you would like to get the notes, !notes, will take you to the Google Drive where I've placed all of my notes. If you are following along on YouTube, the link for the notes is down in the description. It has been brought to my attention that a couple of my links don't work down there. Oh, I have to turn the music off. Hold on. It is distracting for those who watch live. But yeah, so it's been brought to my attention that a few of the links do not work down there, but I am trying to go and fix those. Like, for instance, the tutoring link. I do tutor. It is one-on-one tutoring, so there is a fee to it. But I do tutor. I have tutoring available as a service, and the link for that was broken. Luckily, someone brought that to my attention today. So if anybody's interested in that, I know the semesters are pretty much winding up for a lot of U.S. citizens and European citizens as well. So, but I don't know if anybody would still just like to, chat with me or to talk about whatever. You can utilize that service. What else is there? Yeah, I think that's it. But if you are following along in person, you have the benefit of being able to interact with me, ask me questions. I usually try my best to keep up with chat. Sometimes I miss things, so the best thing to do to ask me a question while you are watching live is to write !ask and followed by your question, and then it will go to a separate screen where I can keep track of it, and either my mods or I will be able to take note of it. Please ask one question at a time so that my mods and I can move it from one column to another. It only accepts one question at a time until we approve it. So, yes, that's it. Anyways, let's begin today's quantum computing discussion series. Last week we talked about a few things. If you're following the notes, I'm pretty much just going to read these things with a little bit of discussing the last one there. The last time we talked about the properties of linear operators and their matrix expressions. So the first time we did linear algebra stuff, we wanted to talk about vectors as states, states as vectors. Most time when you learn quantum mechanics, a lot of people have learned linear algebra first, so they will naturally want to use vectors instead of bras and cats. So we kind of equated the two and then talked about the algebras, the things that you could do to those vectors specific to quantum computing and quantum mechanics in general. Yeah, so then last week we talked about matrices and how operators can be, linear operators are like matrices. And again, if you are more familiar with linear algebra, you're going to tend to stick with the matrix formalism for a while. But there is many cases, and we'll talk about that next week, where you don't want to be fully reliant on vectors and matrices. Namely, that's tensored products, which we're going to talk about next week. Tensored products of states is when the vectors and matrices become very, very burdensome if you try to solve it using those. So it's much more comfortable and useful to get used to the bracket notation, but nevertheless. And then we also talked about the orderings and how to apply matrices to states, because ultimately that's what we're doing. We're applying operators to states and then getting outcomes. And as we're going to find out later today, many of those outcomes that we're interested in are energy eigenvalues and eigenvectors of operators or observables. Last week we also introduced the Pauli matrices, which are highly useful in quantum computing, also quantum mechanics. They're everywhere in quantum mechanics. But in quantum computing especially, we talked about how the X Pauli matrices, the 0, 1, 1, 0, has a, that's the NOT gate. It's like the NOT gate in quantum computing. It's a very, very famous and useful gate that people use that was developed, that was pretty much recognized by Toffoli. When he was coming up with Toffoli gate and other gates. And then we also closed on talking about the inner products, orthogonality, and normalization. We talked about the three requirements for inner products. I didn't really mention, I wrote them on the board, but I forgot to put them in the notes for last week. But they are in the notes now, if you're looking at it. But that the requirements for an inner product is if you have two vectors and you take the inner product, they are linear in the second argument. Remember the book used this notation, which makes this one requirement easy to write down notationally, but not so much for the other stuff. So then this is just written as the sum over all of the lambdas times the inner product of v and w as your vectors. Now, then the other thing that we talked about is, and then this was their notation, this notation, the book's notation. Again, we're following Nielsen and Chang, Quantum Computation and Quantum Information. Good book, kind of like a must-have if you're learning quantum computing. And then but then we went back to our normal kind of standard notation for the next one, which was just to say that if you have two vectors and you want to take the inner product of those two vectors, this is also equal to the complex conjugate of the opposite order of those vectors, okay? Which will come into play today. Oh, that's the other thing we're doing today. We're going to talk about the Cauchy-Schwarz inequality, a very useful equality to have. I like that one. And then lastly is 3. The last requirement for an inner product that we talked about last week was if you dot a product with itself, namely it either needs to be greater than or equal to 0, and it's equality only if it's equality if and only if the state v is actually equal to the number 0, not the ground state, not the 0 state, but the actual 0. Because usually a vector, multiplied by itself, inner product of itself should be 1, if it's normalized. And yeah, anyways, we'll get into that more and more. But Hilbert Space is one of those things in quantum mechanics that gets thrown around a lot, and you're not going to say that you don't understand it when you're a freshman, but let's be real. Or when you're your first year of quantum mechanics. You want to say, like, oh, I got it, Hilbert Space, yeah. But in reality, it doesn't make sense until you use it quite a bit. And a Hilbert Space, for all intensive purposes, is, I'm just going to read it from the notes, a vector space where the vectors are states. I mean, that's it. We talk about a space of states. A vector space. We talked about states being vectors, so it makes sense that Hilbert space would be a state of vectors. There are lots of things that a Hilbert space has that I'm not going to go into in very detailed things, but we will talk about a few of the key pieces of it. One being that Hilbert space's vectors are usually equipped with inner product properties. That is, those 3 requirements that we just listed on the board. Those are required for inner products. Hilbert spaces have vectors as states, space of states, where those 3 requirements are met. That's a very important property of the Hilbert space. Hilbert space also have an analogy to the Pythagorean theorem, built in amongst other things. So we have these other properties of the Hilbert space, but for all intents and purposes, you can just think of it as a space of states. And then those states have to follow very specific rules. But let's see here. As a complete inner product space, yeah. So inner product space, right, yep. Mentioned this. A few helpful remarks is the following. Think about an outer product. We need the outer product for something kind of specifically. We talked about inner product, but what's an outer product? What if you had 2 vectors, w and v, and they looked like this? Well, this has like a form, right? This has a form, and it's an operator. It has an operator form. Looks like a matrix. And it's very helpful for a lot of things. Namely, one thing that you'll use a million times when you're doing quantum mechanics that we hinted at last time, and that is the completeness relation. The completeness relation is one of those things that just shows up over and over and over again. The completeness relation is follows. You can sum over a set of all vectors, orthonormal vectors I, and that's just the identity operator. I don't know if I can write it like that. Let's see how the authors write it. I wrote it weird in my notes. I just want to make sure that the authors don't say something different than this. Yeah, there we go. Yeah, so I are orthonormal vectors, an orthonormal basis of a vector space. And then you can write them as such. And this is a very interesting thing. What happens if we want to apply it to a vector? It's an operator, right? So let's apply it to a vector. Let's apply it to a vector v. So we have some vector v, some state v. And we'll have I applied to I, or I on the outer product of I, and then applied to V, and we get this inner product right here. So what's interesting about this, just using quantum mechanics as the space of square, yeah, that's, I didn't want to talk about that because those are not, those are not like normal, not like what you talk about undergraduate, but it's true. As he said, it's true. I remember there's such a thing as a real Hilbert space, so never mind. Yeah, I don't remember exactly what that means. But anyways, let's keep plugging along. But now we have an inner product right here. So all we did was we took a vector v and we multiplied it by our identity operator. Nothing crazy, nothing weird about that. But then when we did that, we get this number here. This is an inner product of v and I. So we actually get a number. And the way that this could be translated is now we have some, number, vi, times a new state. And what we've done is changed bases. We went from this v basis, this v vector, and we went to a different basis, an I vector now. There's no more v vector here. There's just this product of v with I, okay? Or inner product with vi. And you get, like I said, a real number, a scalar. I don't want to say real, a complex number. I don't mean real as in the real number system. I mean real number as in not a vector. That was a terrible phrasing. Okay, so now let's do the Cauchy-Schwarz inequality. Okay, this is a fun one. This is one of the quantum computing or quantum mechanics like little side proofs that you get. That's really cool. So let's take two vectors. Okay, v and w. These tend to be the vectors of our choosing. So we have v and w. And w. And the idea is, let's make a orthonormal basis set I, just like we had before, such that if we were to, list out all of the i's, basically when you're doing a normalization process like Gram-Schmidt, I know we didn't really talk about it last time. I mentioned the Gram-Schmidt orthogonalization is a means to orthogonalize your set of vectors so that you have an orthonormal set of vectors, right? One of the things we do is we take the first set and first vector and we set it equal to something of the following form, where you have the 1 over the norm of a vector. So for our purposes, we're going to have the norm of the vector of w, which remember from last week, this was what we defined to be the norm, times the vector itself. Or the state itself, I should say. So now we say, okay, so this is the first element. Let me just draw an arrow because I don't want it to be confused with equivalent. So we have this as the first element, and then we orthogonalize things from this. Everything with Gram-Schmidt orthogonalization requires you know the original state, and then you can make an orthonormal set based off of the relationship. What is that called? Recursion? Is that right? You make an orthonormal set based off of recursion. So we can do a recursion process and make a whole orthonormal set, but we're going to define this one to be the first one, and then we're going to make everything orthonormal to that. So that's just a side note. But now if we take those, if we take what we've done here, and we say, what happens if we multiply the inner product of v with itself and w with itself? What do we get? And this is an interesting result, okay? First, let's start by adding a completeness relationship in between the v, okay? So we're going to have, we're going to insert our identity operator right here, v, I, v, and then w, w, okay? So all we've done, I should probably box this or something because now it's in the way. But all we've done here is just taken the vector and inserted a 1 in the middle of this vector right here. Now, we know that I is an orthonormal set as long as we add up over all i's. But what if we say, okay, we're going to take the first one, just the first one, and then we're going to do away with the rest of them, okay? Well, then we know, the only relationship we can draw is that this is going to be bigger than this side, right? This left-hand side is going to be bigger than the right-hand side because we're only taking one of these. We're taking all the other ones that make the orthonormal set and we're tossing them away, okay? So now our relationship becomes greater than or equal to, and we get this, we're going to say, let's take one of these, and that one we take is the first one, So then we can rewrite this as the following. V, W, W, V, all divided by W, W. Now again, you're going to have an I from here and an I from here, so you'll have two of these. So you square this, which is why we get this down here. There's also this term at the end, so we get W dotted with itself. This W dotted with itself is just a number greater than 1, or greater than 0, or equal to 0. So we're just going to cancel these away, because they're just numbers, and they're the same number. And then what we're left with is VW. But remember, I also said you could write this as a complex conjugate in the opposite direction. So we'll have VW complex conjugate. Right? So what does this turn out to be? Well, this is just going to be, I was making the notes for this, I forgot the term. Can someone please remind me what the term is for this? I can't believe this. I was making the notes, I forgot about it, I was like, I gotta look it up. It's not squared, it's something else. It's square modulus, that's a really fancy name. There's another name for it. It's complex conjugate squared or something like that. Nevertheless, it's this value right here. It is the amplitude. It's definitely the amplitude. But anyways, of the it's not the amplitude. It's the probability of measuring V and W. Okay, we're not gonna do it. The cool thing is this will come up a lot when you're actually trying to do measurements, right? Where you're gonna actually take one state and dot it into another state to figure out what type of amplitudes of probability be. You need the complex conjugate squared in order to get the actual probability. Just dotting the two together will just give you the amplitude. But the cool thing is actually if you take the inner product of V and the inner product of W, you can actually draw the relationship. I'm going to write the whole relation up here, right? Where you have V, just in case anybody needs to see it all in one line. That if you take the inner product of V and the inner product of W, this is going to be greater than or equal to the complex conjugate squared of V and the inner product of V and W together. Which is a very interesting reality that we have here. But nevertheless, this is very helpful and useful. Maybe there's some people in chat who have an idea of where this might be more beneficial besides amplitudes, but that's just how I always saw it. If you take the probability amplitudes of V and W with themselves, it's going to be greater than or equal to the probability of V and W. But there's lots of cool, what am I trying to say? There's lots of cool applications of this. Where are we at now? Are we on to eigenvalues? We are. We're on to energy, or on to, not energy. We're on to eigenvalues and eigenvectors. So again, if you've studied a lot of quantum mechanics, you know what eigenvalues and eigenvectors are. But for the rest of us, let's talk about eigenvalues and eigenvectors. So we have operators, right? And most common operators that you might experience would be things like the Hamiltonian, or observables like spin or momentum or things like that, where you actually have an operator and you're applying it to a state and you're trying to get a value that you can actually measure. Well, we have formalisms for this, all well known, and let's start by talking about what an eigenvector is. So, especially since we've been sticking close to this idea of vectors as states and operators as matrices and blah, blah, blah. So an eigenvector is a non-zero vector V. So a non-zero vector V, such that the operator A acting on V yields an eigenvalue of V. We're going to use V's as, so a common notation is that the eigenvector V will have eigenvalue V as well. That's kind of a common notation. But the idea is that if you act on a vector or a state with an operator, you can yield, if this vector is an eigenvector, you'll yield what's called an eigenvalue. So the question is, what's an eigenvalue? Well, eigenvalues are more specifically associated with each of the operators themselves. In fact, the big thing about quantum mechanics is trying to find the eigenvalues of a given observable. So if you're given a Hamiltonian, you might want to find A, if you can diagonalize it to get the eigenvalues, or B, if you can get eigenvalues, period. Okay? Basically these numbers. You want to get these numbers from this observable. So how do you do that? Well, one way that we use to do that There's lots of ways for diagonalizing Hamiltonians. We're just going to kind of stick with the usual way of finding the determinant of the matrix, known as the characteristic polynomial. That's what this is, defined as the determinant of the matrix, which is A minus lambda I, where lambda is going to be the eigenvalues, specifically when this is in fact equal to 0. That's the goal. You'll find a characteristic equation that'll be, you know, however dimensional your matrix is will tell you how many eigenvalues there are. So if it's like a 2 by 2 matrix, then you're just going to have 2 eigenvalues, right? And yeah, so then the idea is, can you extrapolate the lambdas out of this characteristic equation that you get from taking the determinant of the matrix, which is the result of the operator A minus lambda times the identity. Now, you can think of a diagonal representation of a matrix operator A. So A, well, and like this is only relevant to operators that are diagonalizable. That's a thing. Like you need to have a matrix, an operator that is diagonalizable if you want to find those eigenvalues. But if it is diagonalizable, you can write a form like this, where you have each element. This is one of the ways where we see this outer product as a matrix, where you can sum over all of the different pieces of the matrix, and each different piece will have an eigenvalue associated with it. Okay. I don't think I did it in my book, but consider an example of, you know, the polymatrix for Z. Obviously diagonalizable. Do you guys know what the eigenvalues of that matrix are? Like if I were to just say, what's the eigenvalues of the matrix for the Z matrix for the poly spinner, or poly spin matrix? I don't know what you call it. What do you call it? Poly matrix for Z in the Z basis. What would you say are the eigenvalues? 1, -1. Very good. Yep, that's it. That's the eigenvalues. It's diagonal, so the values on the diagonal are in fact the eigenvalues. And this is just the mathematical representation of that. Now, the process of finding eigenvectors. So suppose you just have an operator and you don't have anything else, and you want to find eigenvalues and eigenvectors. This is a common thing that first-year quantum mechanics students will do for the first few weeks. And the one way we can do that is the following. If you have this relationship right here, then you can also think of the following way. If V is the eigenvalues, we'll write VI like that. So you can imagine that there's multiple eigenstates, or eigenvectors, and multiple eigenvalues. Then you will get something that looks like this. The eigenvectors will solve the solution, will be the solution of this equation. Now this should start to look familiar. Does this look familiar to anything? This should absolutely start to look familiar. But this should look familiar because we see many places where this shows up. Let me give you one. And I told you this at the beginning of today's stream, that we're going to see this today. And this is a fun one to have. Fun one to pull out of your booklets and to show people. What if we start with the Einstein energy relations? And of course we don't want to do just the massless one. Whoa, c squared c to the fourth.
Anubis.
Okay, so the Einstein energy relationship. Imagine, so let's square it firstly, because I mean, who wants to deal with this? Am I right? So then we square it, and then let's quantize energy and momentum. What happens if we quantize energy and momentum? So energy is going to take the following form. Oop, not a vector, an operator. If we write the operator form of energy, it's going to look like I h bar d dt. Hopefully you guys see some of this stuff in like Lagrange or in classical mechanics as just like a closing thoughts before you leave the class. You get to see the quantized forms of this stuff. Okay, cool. So this is the energy. Wait, energy is not an operator, is it? No, it's just E. Yeah, just E. Just E. Natural units, true. The momentum. Welcome to the channel. Math my entire life. I'm almost done with the math. Abdullah and Dharma, thank you for the follow and welcome, welcome. Okay, so lastly we want to write, how do we rewrite Einstein's energy momentum relationship? Well, let's rewrite it now with our quantized form. We'll get I h bar d dt squared. This is kind of more specific when it's applied to a state. So let's apply it to a state. Or more specifically, let's apply it to a field. I think I wrote a state, but we're just going to write a field there for now. We'll just talk field theory. I'm not talking specifically about any type of field theory, just field theory, okay? So the operator acts on a field. And what is this going to be equal to? This is going to be equal to negative I h bar squared c squared plus m squared c to the fourth, and if we act on as a field on one side, we need to act on the field on the other side as well. And this is what we get if we want to do energy and momentum as quantized forms, but this is still Einstein's relativistic energy equation, just written as quantized in its quantized form. Now, if we rearrange, we're going to square everything. We'll have some i's to deal with, so we'll deal with the i's. This term will be negative, this term will be positive, blah, blah, blah. I'm going to pull this over to this side. I think we're just going to manipulate, move everything around. And what are we going to get? Well, we'll get 1 over c squared d dt minus this thing, gradient. Forgot my squareds in the notes. You'll have to add them. Sorry. And then apply that to a field. And add our last term here, MC hammer times the field is equal to 0. Now we can also combine this term into the famous D'Alembert. Anyone know where this is going? Forgot the square. I didn't forget the squared. I said MC hammer. Did I forget the square somewhere? Oh, I did on this term. You know what, Tyrion? Anyway, so this is the D'Alembert. If we write down the D'Alembert, we get the box squared minus this term, which I'm just rewriting as mu, because who wants to write all that many terms, times the field is equal to 0. What's this? What's this? Here we have a D'Alembert, which is an operator. Here we have some mass times identity, blah, blah, blah. But we just get back to the original eigenvector situation, right? This is the same form as the one that we talked about before, minus lambda I times VI, 0, right? This is another hugely applicable thing that is all related to all of this, and that is, this super famous one. Right? Again, just rearrange it. So this shows up, like this eigenvector thing, like I might have just shown you like this, like, oh, just grab the eigenvectors from it. But this is so much deeper than that. This eigenvector formula is like the basis for so many things in quantum mechanics and quantum field theory. We have the Klein-Gordon equation. We have the Schrodinger equation. The same thing. How do you get the Dirac equation? Well, you take the square root of this thing, which I did in the YouTube short. Like we have all of that stuff, all from this like simple thing that looks kind of like. Like, oh, okay, Eric, that's how you find eigenvectors. Cool. You learned this like your first week of quantum mechanics in college, but you don't ever get to see any of this stuff until after you've done with everything. But it's just really cool to see how like this one form that you use to find eigenvectors actually applies to the Klein-Gordon equation, Schrodinger equation, Dirac equation. All those three are very, very closely linked, but yet, really cool, powerful equations. All right, that's it for today. As far as the discussion series goes. So if anybody has any questions, now's the time to ask them. I'm going to put